We saw in the last video that we could have a pretty complicated circuit, and through a series of source transformations we can whittle it down to basically a voltage source in series with a resistor, or a current source in parallel with a resistor. So even if we have some kind of, let's say we have a black box that has a big complicated circuit with all sorts of resistors and current sources and voltage sources, and let's say we have no idea what's inside of here. This is going to have some Thevenin equivalence. And so basically that means no matter what's inside of this black box, this is basically going to behave like this. So we don't necessarily know what this R Thevenin and what this V Thevenin is, but we can figure this out actually. And if we were to connect, say, some kind of a load resistor, and if this was, say, a device that was delivering power to this load resistor, then depending on what sort of the intrinsic value of this source is, so in other words, how much voltage is it providing and what's the internal resistance of this source, we can figure out what load resistor to put here to maximize the power that's delivered by this source. So this is the idea of maximum power transfer, and we use this alongside of Thevenin equivalence when we're doing black box testing. So if this is V Thevenin and this is R Thevenin, what we're really doing here is we are saying what load resistor can we connect to this terminal to complete this circuit in order to maximize the power in this circuit. So I'm going to call this RL for load resistor. Okay, so this is something that we can tweak. So if we had some kind of a black box like this, we could connect a resistor to these terminals that are poking outside of the black box. Even if we can't access or see what's inside of here, we might actually have something that's like this going on, but it doesn't matter because it's going to behave like a Thevenin equivalent circuit. Okay, so how do we figure out what this kind of magic number is for the load resistor to cause the circuit to deliver a maximum voltage and current to this particular load? So let's do a little bit of math here. So we know that for this circuit, since we have R Thevenin in series with R load, the equivalent resistance between these two is just going to be the sum. So if we have that R equivalent is equal to R Thevenin plus R load, and we also know that through Ohm's law, V Thevenin is equal to I, so the current that's going around this loop, times R equivalent. So this is going to be the current in the loop, I'll label this as just plain I, times our R equivalent, which is R Thevenin plus R load. Okay, great. So then if I rearrange the terms here, this implies that the current is given by V Thevenin divided by R Thevenin plus R load. Okay, great. So if I can come up with an equation for the current, I can now find the voltage drop across this load resistor by using Ohm's law at this resistor here. So I'll say at the load resistor, the voltage drop of the load resistor, VL, is going to be given by Ohm's law, so I, because I is the same everywhere in the circuit since it's in series, times just the load resistance. So I came up with an equation for I, it's this, so I can take this and substitute it into this I. So this gives me V Thevenin over R Thevenin plus R load, and then I take that term and multiply by R load. Okay, so now I have an equation for the voltage drop across the load resistor here. All right, great. So what am I trying to do? I'm trying to maximize the power that's delivered to this resistor. So the definition of power, if you recall, power is current times voltage. So if we are kind of zooming in on this load resistor, we want to know the power that is delivered to that load resistor, and that's going to be a function of the current that's going through the circuit and the voltage drop across the load. So that would be VL. And we just found an equation for that. We found an equation for I, it's this, and we found an equation for VL, it's this. So I'm going to take this I and I'm going to substitute it in here. I'm going to take this VL equation and I'm going to substitute it into here. So this is going to give me for I V Thevenin over R Thevenin plus R load, and that I'm going to multiply by my equation for voltage drop across the load, which was V Thevenin times R load over R Thevenin plus R load. Great, so this is my I term and this is my VL term. So if I simplify this, I've got two V Thevenins in the numerator, so I can write that as, this is V Thevenin squared times R load over R Thevenin plus R load quantity squared. Okay, let me go ahead and write this as, this is going to be my power as a function of R load. Okay, so this is function notation, not multiply. And the reason why I'm doing that is because, remember, we're trying to maximize this function here. So if I'm going to maximize that, how would I do that? Well, I can use calculus. I can take the derivative of this and set it equal to 0. So let's go ahead and do that. Let's take the derivative of our power in terms of R load with respect to R load. Okay, so then this is going to be V Thevenin squared is my constant, so I'm going to pull it out of my derivative. I have D with respect to RL of, here's my term with the RL in it, R Thevenin plus RL quantity squared. Okay, so my V Thevenin I was able to pull out of the derivative because this is a constant with respect to R load, but this term here has R loads in it, so that means I need to keep this in to take the derivative. So I have a fraction here. You can use the quotient rule. I'm going to use the product rule because I like it better. So this is going to give me, if I take the derivative of my first term, R Thevenin plus RL to the negative 2 plus RL times, I'm going to take the exponent and I'm going to multiply by what's inside the parentheses. I'm going to reduce the exponent by 1, and here is my derivative of power, dp drl. Okay, great. So what I want to do, if I want to maximize the power function, I take the derivative and then I'm going to set it equal to 0. So if I set this equal to 0, this is going to be 0 is equal to V Thevenin squared times R Thevenin plus R load to the negative 2 minus 2RL times R Thevenin plus R load to the negative third. And now if I bring one of these terms over to the other side, this is going to give me 1 over R Thevenin plus R load squared is equal to 2 R load times, or divided by R Thevenin plus R load cubed. Okay, so I've got these two terms multiplied together. I know that's not going to be equal to 0, right, because that's Thevenin. So this one I set independently equal to 0. And then when I do that, I'm going to bring 1 over to the other side. I express this as a fraction, so instead of writing the negative exponent, I just put it in the denominator. And now I can cross multiply this, and I get R Thevenin plus RL cubed is equal to 2RL times R Thevenin plus RL squared. Okay, great. So this tells me that R Thevenin plus RL cubed divided by R Thevenin plus RL squared is equal to 2RL. So in other words, if these things cancel, this is just going to be equal to 1 R Thevenin plus RL. Okay, great. So my equation is now this part. So that means that if I subtract an RL over here, I'm going to get that R Thevenin is equal to RL. So if my R load that I connect to my circuit is equal to my R Thevenin, that is what's going to give me the maximum power transfer. Okay, so that's the takeaway here. If RL is equal to R Thevenin, then maximum power is delivered to RL. Okay, so if you have a circuit, no matter how complicated, if you whittle it down to its Thevenin equivalent, then you will have that R Thevenin for the entire circuit. So if you connect a load resistor with the same value, that is how you ensure maximum power transfer. So let me know if you have any questions about that concept. In the next video, we'll talk a little bit more about black box testing.